All right. I need you to... All right. I need you to forget everything you think you know about speed. Because here's the thing. 299,792,458 meters per second. That's the speed of light. You've heard it before. You probably nodded and moved on. Yeah, speed of light, cosmic speed limit. Einstein, cool. But have you ever actually stopped and asked, why? Not what is it? Why is it the limit? What physically stops you from going faster? Is there some invisible wall out there? Some cosmic cop pulling you over? Because if you actually chase that question, if you really refuse to let it go, you end up somewhere that will genuinely mess with your head. You discover that the speed of light isn't really about light at all. It's about the actual architecture of reality, and once you see it, you can't unsee it. Let me take you there. But we're not starting with light. We're starting with something you've known since you were a kid. Things fall. Drop your phone right now. Actually, don't. But if you did, it would fall about 16 feet in the first second. Galileo measured that. Everything falls at the same rate. Ball. Rock. Your dignity after tripping in public. 16 feet. 1 second. Now look up. The moon. It's just hanging there. Orbiting. Not falling. Right? Wrong. It is falling. Every single second the moon is falling toward the Earth. But here's the trick. It's also moving sideways. Fast. So it falls toward us but keeps missing. That's literally what an orbit is. The most elegant miss in the universe. Just constantly falling and constantly overshooting. Forever. And this is where Newton had one of the greatest ideas any human has ever had. He looked at that moon and thought, what if the same force that makes my apple fall is the same force keeping the moon in orbit? And what if that force gets weaker with distance? Specifically, weaker by the square of the distance. So he did the math. The moon is about 60 times farther from Earth's center than we are standing on the surface. If gravity follows an inverse square law, then gravity at the moon should be 60 squared, 3,600 times weaker. Things fall 16 feet per second on Earth. So at the moon's distance, the fall should be 16 feet divided by 3,600. He checked it against the moon's actual orbit. It matched. Perfectly. Two completely unrelated facts, how fast a rock falls on Earth and how fast the moon orbits, suddenly connected by one single law. That's not just smart. That's the kind of insight that changes civilization. And Newton didn't stop there. He calculated what shape orbits should take under inverse square gravity and got ellipses. Kepler had already measured that planets move in ellipses, but he had no idea why. Newton just explained it, almost as a side effect. Then the tides. Why do we get 2 high tides a day instead of 1? Think about it. If the moon just pulls water toward it, you'd expect 1 bulge on the moon-facing side. But we get 2. Newton figured it out. The water on the near side of Earth is closer to the moon, so it gets pulled more than the Earth itself. The water on the far side is farther away, so it gets pulled less than the Earth. Earth gets yanked forward, and that far side water gets left behind. 2 bulges, 2 tides. He explained why the Earth is round. Gravity pulls everything inward. Why it's not perfectly round. It's spinning, so the equator bulges out. Why the sun and moon are round too. 1 law. Dozens of mysteries solved. And this is the pattern of science. Each answer becomes a tool that unlocks the next question. Newton called it an avalanche of discoveries. And honestly, that avalanche has been rolling for 400 years, and it's only getting faster. But here's where it gets wild. As measurements got more precise, scientists started testing Newton's law against the moons of Jupiter. They tracked those moons obsessively, predicting exactly when each one should appear and disappear behind Jupiter, based on Newton's equations. And the predictions were wrong. Not by a lot. By about 8 minutes. Sometimes the moons showed up 8 minutes early, sometimes 8 minutes late. Now most people would have panicked. Newton's law is broken. But a guy named Romer noticed something strange. The moons were early when Jupiter was close to Earth, and late when Jupiter was far away. And instead of doubting gravity, he doubted something else. He said, what if light isn't instant? What if it takes time to travel from Jupiter to us? When Jupiter is closer, the light arrives sooner. When it's farther, the light takes longer. That 8-minute discrepancy, that's the extra travel time for light. He was right. And just like that, by trusting Newton's law and refusing to throw it out, Roemer discovered the speed of light, without ever directly measuring light itself. That's the beauty of science. When one law is right, it becomes a lens that reveals something new. And this discovery, that light has a finite speed, set the stage for the single strangest realization in all. But wait, why? Why is there a speed limit at all? And here's where most explanations fail you. They say because Einstein said so, and leave it there. But there's a deeper way to see it. You think of space and time as separate things. You move through space, time passes, independent, unrelated. But they're not separate. They're one thing, space-time. And here's the mind-blowing part. You are always moving through space-time at the speed of light. Always. Right now. Even sitting in your chair. But your motion is split between space and time. If you're sitting still, all of your motion goes through time. You're hurtling into the future at maximum speed, 1 second per second. But the moment you start moving through space, you're diverting some of that motion away from time. You're now moving through space and time, which means you're moving through time slower. The faster you move through space, the slower you move through time. And there's a limit. If you move through space at the speed of light, you'd have zero motion left for time. Time would stop. That's why photons don't experience time. From a photon's perspective, it's created and destroyed in the same instant. The entire journey, even across billions of light years, takes zero time. You can't go faster than light because you can't go less than zero through time. There's nothing left to trade. That's the wall. And look, I know what you might be thinking. This is all very poetic, but is it real? It's the most tested thing in physics. Particle accelerators push particles to 99.9999% of light speed every single day. And every single time, it gets exponentially harder to push them faster. Exactly, as Einstein predicted. GPS satellites, the ones your phone uses right now, they move fast and sit in weaker gravity, so time passes differently for them than for you on the ground. If engineers didn't correct for relativistic time dilation, your GPS would drift by kilometers within a day. Every time you use Google Maps, you're relying on Einstein being right. Muons, subatomic particles created when cosmic rays hit the upper atmosphere. They have incredibly short lifetimes. They should decay before they ever reach the ground. But they're moving near light speed, so time slows down for them. They live longer. More of them reach the ground than classical physics says should be possible. We measure this. It matches relativity perfectly. This isn't philosophy. It's engineering. It's measurement. It's fact. So here's the full picture. The speed of light isn't a speed limit that was imposed on the universe. It's a consequence of how the universe is built. Space-time has a structure, and that structure includes a maximum rate at which cause can produce effect, a maximum speed of now. Light happens to travel at that speed because it has no mass. But if light didn't exist, the speed limit would still be there. It's a property of space-time itself, not of light. And the story of how we figured this out, that's the real miracle. Newton watching the moon fall, Roemer watching Jupiter's moons flicker, Einstein sitting in a patent office imagining what it would be like to ride a beam of light, each one building on the last, each discovery cracking open the next door. 400 years of that avalanche, and we're still riding it. The speed of light isn't just a number. It's the deepest clue the universe has given us about what it actually is. And the fact that a bunch of primates on a tiny rock figured it out, that's the real speed of light story. Of physics, once we could measure the speed of light precisely, we noticed something that should have been impossible. Light always travels at the same speed. Always. No matter what. Let me make sure you feel how weird this is. You're standing still. You turn on a flashlight. You measure the light. 299,792,458 meters per second. Great. Now you hop on a spaceship moving at half the speed of light. You turn on the flashlight in the direction you're flying. Common sense says the light should be going at light speed plus half light speed. Like throwing a ball from a moving car. The ball goes faster because the car's speed adds to it. But you measure the light, and it's still 299,792,458 meters per second. Exactly the same. That can't be right. So you speed up to 90% the speed of light. Flashlight forward, measure. Same speed. 99% the speed of light, same speed. 99.9999% the speed of light. Same speed. The speed of light does not add to your speed. It doesn't care how fast you're going. Every single observer in the universe, no matter how fast they're moving, measures the exact same number. If this doesn't bother you, you're not paying attention. This breaks the fundamental rules of how we think motion works. So Einstein asked the only honest question. If the speed of light is always the same for everyone, what has to give? And the answer is everything else. Time and space are not fixed. They bend. They flex. They warp. And they do it specifically to keep the speed of light constant. When you move faster, time literally slows down for you. Your clocks tick slower. Not metaphorically, actually slower. And distances contract. The space in front of you physically compresses. And here's the kicker. The amount they change is exactly the right amount to make the speed of light come out the same for you, no matter how fast you're going. Let me say that differently. The universe rearranges time and space, bends them, stretches them, compresses them, to protect one number. The speed of light. That's how fundamental it is. Reality itself reshapes around it. Now what happens if you try to actually reach light speed? You accelerate. You get faster. But the closer you get to the speed of light, something strange happens. It gets harder. Not because your engine is weak, not because you ran out of fuel, but because you become harder to push. Your inertia, your resistance to acceleration, increases. The faster you go, the more energy it takes to go even a tiny bit faster. And as you approach light speed, your inertia approaches infinity. To actually hit the speed of light, you'd need infinite energy, which doesn't exist, so you can't get there. Not because of some rule someone made up, because the geometry of space-time literally won't allow it. Light travels at that speed because photons have zero mass. They must move at that speed. They have no choice. But anything with mass, you, me, a spaceship, a grain of sand, can get arbitrarily close, but never quite there. The universe won't let you. And honestly, that's kind of beautiful.